Thank you for giving me a chance to talk here. I'm Yuhiko Aoyama from the University of Tokyo. Today, let me talk about this title, Theoretical Modeling of Hydrogen Line Emission from Accreting Star and Planets. They are my collaborator, Masahiro Ikoma and Takayuki Tanigawa. Yes. In the title, I will, as I show in title, I will talk about accreting star and planet. But at first, mainly I will talk about the accreting gas giants. This is a result of direct imaging observation. At the center of this figure, there is accreting star, a pre-main sequence star, PDS-70. And in this figure, blue color shows photo detection of near infrared, and red color shows detection of H-alpha photon. Here, there is the point source-like feature, and this is thought to be the planet, accreting planet emission. Actually, several newly forming planets has been observed, but this is one of the special ones because this planet is also detected in not only near infrared, but also H-alpha emission. Hydrogen line, including H-alpha, is emitted by the hot gas because source of hydrogen line is excited hydrogen. Excitation of hydrogen requires hot gas, about 10 to 4 Kelvin or so. So in the protoplanetary disk, there is no hot gas excepting around accreting gas giants because the release of gravitational energy can heat gas to 10 to 4 Kelvin and can emit H-alpha or hydrogen lines. So many people believe that such a H-alpha is indicator of accreting gas giants or gas accretion. However, there is no quantitative study previously. So I will focus on the H-alpha emission from accreting gas giants. Here, I will show the SED, spectral energy distribution of Rickarcin 15b. This is another one emitting H-alpha. The red and green and blue point correspond to the observational results. The vertical axis is flux in Miljansky, and horizontal axis is wavelength in micrometer. These red and green points correspond to the near infrared observation, and the blue one is H-alpha. The lines shows theoretically estimated SED. The black line corresponds to the estimated emission from circumplanetary disk, and pink one corresponds to the estimated emission from accreting planet photosphere. As you see, the red and green point is on the theoretical estimated SED. Namely, the theoretical model can reproduce the near-infrared observation and emission. However, the blue one, H-alpha, is far from these theoretically estimated lines. Actually, the theoretical model assumes the temperature, relatively low temperature of 10 to 3 Kelvin or so. On the other hand, as I said, H-alpha requires much more higher temperature, about 10 to 4 Kelvin or hotter. So, seemingly, these two temperature seems to be paradoxical. So, I will show a schematic figure. It is a candidate of such a paradoxical SED. This is a schematic view, edge-on view of 3D accreting disk. This red one is accreting gas giant, and circumplanetary disk is surrounding it, and gray region corresponds to the planetary Hill sphere. Recent 3D hydrodynamic simulation shows that the gas in the midplane of protoplanetary disk cannot enter the planetary Hill sphere. Instead, the gas in the high altitudes can enter the planetary Hill sphere and falls on the circumplanetary disk. And at the surface of circumplanetary disk, the gas velocity can reach almost a free fall velocity. Then the strong shock is generated at the surface, and the shock heated gas is up to 10 to 4 Kelvin or hotter and can emit a hydrogen line, including H-alpha. Moreover, the shock-heated gas should cool rapidly because the equilibrium temperature at here is much lower than this temperature, 10 to 4 Kelvin. So the mid-plane of circumplanetary disk or planetary photosphere can keep the low temperature of 10 to 3 Kelvin, although the shock-heated gas is 10 to 4 Kelvin. However, we have to check, because of the rapid cooling, we have to check whether the amount of shock-heated gas is enough to reproduce the observed H-alpha intensity. So in this talk, our purpose is following. We want to understand how H-alpha line is yielded in shock-heated gas around creating gas giant. And also, we want to estimate the intensity of H-alpha line and compare it with observational results. And if we can, we want to get some information from the observational results of H-alpha. Okay, this is a model of our this is our model. In this talk, we focus on the shock-heated gas, and numerically we simulate the cooling flow after the shock-heated gas. The initial condition of our model is these two: V0, the pre-shock gas velocity, and pre-shock gas number density. And actually, we want to calculate the radiative transfer in the shock-heated gas, but actually the coolant or cooling source in the shock-heated gas is the radiation or emission of hydrogen line. So the timescale of radiative transfer and hydrodynamics or gas cooling is nearly comparable. So we have to calculate these two at the same time. Also, actually, the electron transition should be included in time-dependent case because the electron level distribution or excitation degree is not in equilibrium state. So I include an electron transition, and also I include a chemical reaction because we want to estimate the ionization rate or number of free electrons. So at first, I will show the numerical result of our model. This is gas flow property after the shock. In this case, the initial parameter is there. The pre-shock gas velocity is 40 km per sec, and gas number density is 10 to 15 per cubic meter. The vertical axis is the depth or distance from the shock front in all three figures. And in the left figure, the gas temperature after the shock is shown. Just after the shock, in this case, the gas temperature reaches 6 times 10 to 4 Kelvin or so, and then rapidly cools via the H2 dissociation and hydrogen excitation or ionization. In the center figure, I show the chemical abundance relative to hydrogen nuclei. Because I assume the hydrogen is in molecular form before the shock, the purple one, molecular hydrogen, is 0.5 at just before the shock, and then the atomic hydrogen is increasing. The black one and red and blue one correspond to the atomic hydrogen, whose principal quantum number is 1, 2, and 3. And the orange and green color correspond to the ionized hydrogen and free electrons. As you see, the excitation degree is not in equilibrium and time dependent. And the right figure, I show the hydrogen line energy flux in the shock-heated gas. The hydrogen line is emitted in deep region and goes towards the shock front upward in this figure. And red one corresponds to the H-alpha, the observed line at the PDS 70b or Recursion 15b, such as protoplanets. As you see, in the post-shock region, although the gas rapidly cools, the significant H-alpha is emitted in this region. I showed only one case, the post-shock gas property, but I numerically calculated for many parameters. This is the result of the parameter study. The vertical axis is H alpha energy flux, and horizontal axis is pre-shock gas velocity. And each color corresponds to the pre-shock number density. But actually, we want to get not energy flux, but hydrogen line luminosity. So we integrate this flux on the wall circumplanetary disk. I assume the precise free fall velocity at circumplanetary disk surface. Then we can convert the gas velocity into the distance from the protoplanet. Then I can calculate, or I can integrate the energy flux, and we can get the luminosity of H alpha or hydrogen lines. This is the result. The color contour shows the H alpha luminosity in watt, and vertical axis is gas accretion rate, and horizontal axis is planetary mass. In this case, I assume the constant mass flux on the whole circumplanetary disk. This depends on the results of 3D hydrodynamic simulation of Tanigawa et al. 2012. Here is the observational data. At PDS 70B, H alpha luminosity is observed at 5 times 10 to 20 watt. It corresponds to the red line in this figure. And also, the planetary mass and mass accretion rate is observed at in IR photons, IR wavelengths. The mass is 5 to 9 Jupiter mass, and mass accretion rate is less than 10 to minus 7 Jupiter mass per year or so. As you see, the gas accretion rate is too low to reproduce the PDS 70B's luminosity. This is because almost all gas fall onto the region far from the protoplanet. Then the free fall velocity is too low to reproduce the H alpha, emit H alpha. On the other hand, if the planet is embedded in the minimum mass solar nebula, not depleted minimum solar nebula, then the gas accretion rate is about 10 to minus 3 Jupiter mass per year or so. So then the observed H alpha at the PDS 70B can be reproduced. But if so, the planet have to or should grow to too massive, and the surrounding gas in the protoplanetary disk should deplete rapidly. So it's not unrealistic one. So I showed another one. In this case, I assume that all accreting gas contribute to H alpha. For example, such a case is realized or established when the gas giant has a cavity in the circumplanetary disk, and then the gas in the circumplanetary disk fall onto the planetary surface, and then a strong shock is yielded on the planetary surface, and all accreting gas can contribute to H alpha. This figure is the same as the previous one, but the range of vertical axis is dramatically changed. Again, this is observed data. H alpha luminosity is 5 times 10 to 20 watt, this red one, and planetary mass is 5 to 9 Jupiter mass, and planetary mass accretion rate is 10 to minus 7 Jupiter mass per year or so. So as you see, in this case, our model will agree with the observational data. So one possibility is the PDS 70B has cavity in circumplanetary disk, and all gas is fall from the circumplanetary disk to planetary surface. Actually, I have some slides about the protostar, but I have no time. So this is my summary. Thank you for attention.
I'll just ask one question. Do you observationally have any information on the width of the line?
What line?
H alpha.
H alpha, yes.
Yes, I'm just wondering how your models are able to reproduce that.
I guess, no, yes. Yeah, in some case, for example, yeah, we assume some, we take some assumption, we can reproduce the H alpha line, observe the H alpha line.
The profile.
Yes.
With this model.
Yeah. Yeah, we need some assumptions, but yeah, then I can reproduce it.
2rj as your inner radius, our larger radii also can also give consistent results, or are they ruled out by your models?
You mean this result depends on the cavity radius? No?
The inner radius.
Yeah, inner radius.
Yeah.
Yes, yes. So yeah, in this case, I assume the gas velocity is in free fall velocity. It is a limit of the inner edge is far.
No, I mean the 2rj that you choose in the model. You assume that the planet is twice the radius of Jupiter. at this stage.
Yes,
Yeah.
that's right. Yes, sorry. Yes, Jupiter. This is a Jupiter radius. No, planetary radius. Sorry. I mean the gas fall from the infinitely far to the to Jupiter radius point planetary
Yes.
surface.
So I'm asking if you'll choose a larger radius, 4
yes.
times the radius of Jupiter, will this be inconsistent with the observations, or can you still have a consistent model with a larger
You mean
radius?
2 Jupiter mass is consistent or inconsistent to the observational result?
Yes. Can I have a consistent model with 4 times the radius of Jupiter?
Yeah, as I know, planetary radius is not observed, so we can choose arbitrary planetary radius. But 2 Jupiter radius is not so bad in model, in some theoretical model. Okay.
Okay.
Thank you.
Couple of comments and questions. First of all, this model what you just show, I mean, and this will also depends on extinction, and it will depend on the temperatures what you are assuming very high temperatures here. And when we do radiative hydrodynamic simulations, we do not get 60,000 K temperatures near the forming planet. I mean, we are talking about the shock front, which can get 10,000 K indeed, but near the planet in the midplane, it goes to 1,000 K, but at the edge of the circumplanetary disk is 200 K. So I also did, as you know, some calculations of this in 2017, and my values are corresponding to what the observers are finding. So those temperatures are much lower, and then they can reproduce the age alpha luminosity if the planet is 10 Jupiter mass or more massive. So I think there is some things here which you might want to look at, like extinction and some other things, and also the temperature calculation. How did you get these temperatures, by the way? Because you said that you run, the simulation was isothermal, so.
Isothermal? You mean the hydrodynamic simulation I based on is in isothermal simulation. Yes, that's right. But I guess it's not so. Our result is not so. Depend on the hydrodynamic simulation, and I guess the
it is
difference
dependent on the temperature, right? Your fluxes are dependent on the temperature. So how do you get the temperatures then if you don't have that information from the simulation?
You mean temperature is the post-shock temperature? Then yes, the result depends on the post-shock temperature. But I guess the difference our result depends on the resolution of spatial resolution. So yeah, in our calculation, no. Yeah, the spatial length is from 10 meter to 100 meter to at most 10 to 5 or 6 meter or so. So it's really a thin region. So I guess in large scale hydrodynamic simulation, we cannot see such a really thin or really small scale hydrodynamic, small scale physics. On the other hand, in your calculation, the temperature is 10 to 3 Kelvin or so. Then the length of the such temperature is continue or keep a bit too long. So in my calculation, the temperature is high, but the temperature is not continue for a long time. But in your case, the temperature is a bit lower, but the temperature keep a bit longer time or longer spatial scale. So I guess your calculation can reproduce the H alpha by low temperature. And in my calculation, the temperature is different, but our calculation can also reproduce the H alpha, I guess. Okay.
Sounds like a good matter for further discussion. I think this is the end of the session. How long do we have for? 30 minutes for coffee. So let's thank all the speakers.
Thank you.